friction is an extremely important force. Friction is what keeps a nail in a piece of wood. Why doesn't the nail just slide right out of the wood? It's because of friction between the nail and the wood itself. So the building you're in is actually most likely held together by friction, unless it's like a brick structure, like arches and things like that. Wood, nails, and screws, they work on friction. They hold everything together. Friction, it's not a stickiness. It's the force which makes sliding difficult. So rub your hands across each other, and that effort it takes to slide across, that's friction. There's no stick there at all. It's just the friction, the sliding that you feel. If you go and put socks on and slide across the floor, a smooth floor, it's friction that slows you down. Aristotle would have thought of it differently. Aristotle would have said, the reason you stopped is because that's just what your nature makes you do, that nature makes things stop, right? He didn't know friction was a force. He didn't recognize it as a force which is actually slowing you down, that without friction, you would just glide forever across the earth. So friction, what factors affect friction? If you rub your hands together, you'll feel friction there. If you put on rubber gloves and rub your hands together, you'll feel way more friction. They're not sticking to each other. It's just the sliding is more difficult. So it depends on the materials that are sliding past each other. And that's why, you put oil in an engine, it reduces the friction between the engine components. There's also a very important second factor which affects how strong friction is. If I rub my hands together, I feel that friction. How can I make the friction much stronger? Push your hands together very firmly. And then the friction is way, way stronger, right? It takes a bunch of effort to slide past each other. So it also depends on the contact force between the surfaces. The contact force, also known as the normal force, just another name for it. It turns out those are really the only two factors that affect friction. In other words, it's not affected by speed. Like if you slide across the floor with your socks on, the friction's not bigger when you're sliding faster than it is when you're sliding more slowly. Okay, it's not affected by speed at all. Also, interestingly, it's not affected by the surface areas. In other words, the areas in contact don't affect how strong the friction is. Let me illustrate that. Take a book, okay, put the book on the table in front of you. I have to hold this thing up to do the same thing. But if I put the book on the surface, I can gauge how much friction there is between the book and the surface. Okay, it's fairly smooth. If I put the book on its edge, like this, now is there more friction or is there going to be less friction? Try it yourself, and I think you'll be fairly convinced that the amount of friction is the same, or virtually the same. Why in the world does that happen? Because you might think that when it's on edge, maybe you think now there's less area and maybe there's less friction now. Or you might argue that now that it's on a narrower area, there's more pressure there, and that might increase the friction. The truth lies between the two, and in fact, there's the same friction either way. So let's have some understanding what's going on here. Friction is produced when two surfaces slide past each other, and the surfaces have a kind of roughness to them. There are little peaks and valleys on the surface, microscopically, I mean. The book surface looks smooth, but microscopically it's rough, and the roughness produces these little peaks and valleys, like you see here. The peaks and valleys produce little bonds between each other, like the little peaks of one surface actually bond with the peaks on the other surface. Okay, so when they push harder together, isn't that going to make it's going to kind of crush them together? And doesn't that make more of the peaks touch each other? Sure, and it gives more of that, what they call micro welds, WELDS. And the microscopic welding that occurs is what causes that sliding friction effect. So increasing the contact makes more of that welding that occurs between them, and that increases the friction that you feel. Now, between the book and the surface, maybe there are a million little weld points. It's probably way more than a million, but just suppose there are a million little weld points there. When I put it on edge, amazingly, there are still the same number of weld points, like a million of them. And that's why the friction ends up staying the same either way. Okay, so friction opposes motion. You try to slide a giant box across the floor, you have to overcome friction to do it. The friction is a force that opposes the sliding motion. That sounds like air resistance. If I wave my hand around, I feel the air resisting my hand. More obvious when you put your hand out of a car window and you feel the air blowing back. That's air resistance. Now, air resistance is definitely stronger the faster the air is blowing past, but friction has no dependence on speed. So no matter how fast you're pushing the box, the friction is actually the same. We'll talk a lot more about air resistance in a coming section. And I already mentioned that friction's not dependent on area. And that's pretty, a kind of a bizarre thing. You think bigger area maybe means better friction. Do wider tires give better traction? Surprisingly, no, they don't. The area has no effect on the friction. Smaller area just means that increases the pressure on those areas, and you get the same number of little micro welds that exist between the roadway and the tire itself. So why don't we just ride on super narrow tires? Why don't our cars have like bike tires then? The traction is just as strong. The friction is just as good. The reason you don't ride on bike tires is because the tires would wear out super fast. It's just to reduce wear. If you rode on bike tires, the tires would wear out, like in a few months or whatever. Wide ones just have more rubber, they last longer. Okay, question. You push a fridge across the floor at a constant speed. I'm assuming the fridge is sliding across the floor, not like rolling or something. Okay, you're sliding a giant thing across the floor at a constant speed. The force of friction between the fridge and the floor, is that force less than your push, equal to it, equal and opposite to your push, or is it more than your push? Pause and think about it carefully. If you said that the force of friction is less than your push, sorry, that's wrong. In order to push something at a constant speed, the forces on it must be exactly balanced. So in fact, the friction and your push are just equal and opposite to each other. In other words, he's pushing with 100 pounds of force. The friction must be opposing it with just an equal but oppositely directed amount of force. Friction, let's say lowercase f. Of course, the friction's actually here, but we draw it from the center just to show how the forces oppose each other. Okay, so again, you've got to read these kind of questions very, very carefully, these word questions. Constant speed. That phrase is screaming at us that this is an equilibrium situation. Constant speed means equilibrium, means the forces have got to be balanced. Next, you push a fridge across the floor at an increasing speed. Now, how does the friction compare to your push? Pause it. Okay, welcome back. Now, I hope that you realize that if you're going to make the box gain speed, that requires your push to be even bigger than the friction. Right? Now you're overcoming friction, and now the force of friction must be less than your push. Right? Now it's accelerating. Now the forces are out of balance, and we're in the realm of Newton's second law, where the object is going to accelerate because the net force on it's no longer zero. So key phrase here is increasing speed indicates to me that the net force on it is no longer zero. There's now an acceleration that the fridge is going to experience. Okay, we talked about friction and some of the puzzles of friction. Now let's understand a huge puzzle of free fall. How in the world can 4 books tied together fall at the same rate as one book? It's just absolutely crazy because 4 books weighs 4 times as much if they're all the same book. It weighs 4 times as much. It's pulled 4 times as hard. How in the world can its acceleration be the same as one book, which has much less force on it? Now we can finally answer it. Look at the picture here. Here's 2 books tied together. It has twice the mass, right? But it also has twice the force. And do you remember what happens if you double the force, but also double the mass? Well, that just gives you exactly the same it's the same effect as one force acting on a single mass. It's the same acceleration either way. So the unbelievable fact that heavier things fall at the same rate is because of Newton's second law. If the mass is greater, then the inertia is bigger. Well, if the mass is greater, then the force is bigger. The force of gravity is bigger. It increases. But you see, the force is bigger, twice as big, but the mass is also twice as big. It's the inertia is increased. And that means that you've doubled the force and doubled the mass, and therefore the acceleration's just as big. Therefore, we have the law of falling bodies. That it just doesn't matter how much the mass is, the acceleration's equal to a fixed value in all cases. Of course, Galileo has to come and measure what that value is, but it's going to be the same for all of these objects, 9.8 meters per second squared. Notice it's because when you take 2 of the mass, two books together, that doubles both the mass and it doubles the amount of force. Compare that to the the guy blowing on these blowing away these balls, right? Here, the mass of the heavy ball is much larger, but the force on it isn't like correspondingly bigger. So in that case, it's big mass but with a small force. So of course the acceleration is little. But with falling things, big mass also goes along with a bigger force, and the two effects cancel each other out. So thank you, Isaac Newton, for finally explaining that puzzle to us, that Aristotle was way wrong on this. Heavier things do not fall faster, and here's the reason why. It's because the heavier things have more inertia as well. And that's why in a vacuum, the coin and the feather fall together. Okay. Now, how much do things weigh? In other words, if I know the mass of something, if I know something has a mass of 1 kilogram, how do I figure out what the force of gravity is upon it? Well, you can do it by dropping it. If you drop it, you'll know what its acceleration is, and then you can figure out how much force there is acting on it. Let me write those things down. If I want to know the force on something, it actually belongs here. Acceleration from gravity alone is equal to what we call g, which is 9.8 meters per second squared. If you've forgotten what that means and how we do the kinematics of it and all that, you should go back to the video with kinematics and motion. But that's the acceleration from gravity. No matter what object you drop a chair, it's going to fall at that rate. So then how big is the force from gravity? Okay, let's think about this. How do we figure out F? Well, you can find the force on an object by taking the object's mass and multiplying it by whatever acceleration it's experiencing. If something's falling at the rate of g, then I know that the force on it must be equal to the object's mass multiplied by g. In other words, I would like to know how much this book weighs. Okay. Now, one way to do that is to let it fall and measure its acceleration. I already know what it is. It's 9.8 meters per second squared. That means the force due to gravity on the book must be equal to the book's mass multiplied by g. It's true even if it's just resting in my hand, because it's not like gravity turns off just because I'm holding the book. So even when the book is just here in my hand, the weight of the book, the force of gravity, is still the mass of the book multiplied by g. Okay. Oh. The weight of an object is equal to the mass of the object in kilograms multiplied by the number 9.8, little g. Okay, let's see how this plays out. What's the weight of 1 kilogram of figs? Pause it and work it out. Here's the answer. Weight is equal to the mass multiplied by g. In this case, that's 1 kilogram, multiplied by the free fall acceleration of, it's 9.8, but remember we usually round up to 10 for simplicity. So 1 kilogram weighs 10 newtons. The joke is 1 kilogram of figs weighs 10 fig newtons. Okay? So, again, mass and weight aren't the same thing. A kilogram of figs has a kilogram even out in deep space. It weighs 10 newtons next to the Earth. Do you think it'll weigh 10 newtons if you take it to the moon? No way. Moon's gravity is less. The g value on the moon is like 3.6, not 9.8. So on the moon, g is way smaller, or moon's gravity is less, and the kilogram of figs on the moon are only going to weigh, like 3 newtons. Or like 2 newtons, I think. Okay, so here's Nellie Newton. She's on a snowboard. Her weight is equal to her mass multiplied by g. So from this point on, whenever we write the weight of something in a picture, in a force diagram, I'm really never going to write W. I'm always going to write M times G, because that's how much something weighs. It's mass times G. Now, she is just resting on level ground here, and that means her normal force, the normal force on her from the snow points straight up and just balances out her weight. This means she is happily in equilibrium. Forces are balanced. In other words, N minus mg is equal to 0. In other words, so all I've done there is write out the total amount of force. I added the forces together. N up, mg down, hence the negative sign. This means that the normal force on her is just exactly balancing her weight. And that's the situation on you right now, probably. You're probably sitting or maybe standing watching this, and the support up on your feet is exactly balancing the weight of Earth's gravity pulling you downwards. That's the situation in equilibrium. If you're exercising and jumping around right now, then the push from your feet can be larger than your weight. That's how you jump off the ground. If you want to slide down a hill, what's going on there? Well, you see, this is a situation where there's no way that the net force on Nellie is equal to 0. No way. Why not? Couldn't N be just, if she weighs 100 pounds, couldn't N be 100 pounds and the forces balance? Well, there's no way these forces balance because they're not in opposite directions, right? The only way forces can balance is if they're opposite each other. The only way two forces can balance is if they're exactly pointing opposite directions. Here, the two forces are in different directions. Do they add up to 0? Well, let's just see. I mean, obviously they don't. Well, let me add them up and see. I hope you remember to add vectors together. You do head to tail. Head to tail. If you don't remember that, go back to the section on adding vectors. So to add vectors, I would add, let's say, mg, her weight, onto the normal force. And let's see what I get. Remember, to add it up, I would take mg and drag it over here. Take the weight and put it head to tail on the normal force. And that would put it like right about there. And so the net force is found by connecting here to there, like so. That would be the net amount of force. The net force sure isn't 0. In fact, the net force is pointing down the incline. And I hope that makes sense. The net force is pointing down the incline, indicating she's going to start accelerating down the incline. Remember Newton's second law, which says that the net force on a thing is directly proportional to the acceleration. Let me write it this way. The acceleration is directly proportional to the net force. If the net force points down the incline, then she's going to accelerate down the incline. So this is why something will go down a hill. It's because the net force on the object actually points downhill and causes a downward acceleration. Okay, next topic is going to be on non-free fall. We know that things fall if there's no air resistance at the rate of 9.8 meters per second squared. What if there is air resistance? That's the next topic.